Let's take a look at another example of hypothesis testing with two samples. A researcher wishes to see if the average weights of newborn male infants are different from the average weights of newborn female infants. She selects a random sample of 10 male infants and finds the mean weight is 7 pounds 11 ounces and the standard deviation of the sample is 8 ounces. She selects a random sample of 8 female infants and finds that the mean weight is 7 pounds 4 ounces and the standard deviation of the sample is 5 ounces. Can it be concluded at alpha equals 0.05 that the mean weight of the males is different from the mean weight of the females? Assume the variables are normally distributed, then compute Cohen's d. Okay, so what we have here, again, is this is going to be a two-sample test because we have the group of the male infants, the group of the female infants, and there's no overlap between the two. We're trying to determine, is there a difference between these two independent populations? So we can use some subscripts, for instance. So we could say mu sub male. This would be the mean of the males, and we can use, say, mu sub f, and this would be the mean of the females. So we can indicate what our subscripts will be. So we have our null hypothesis. This says that these two are going to be equal to each other, that there's no difference between the mates, between the weights of these two. Then we have the alternative hypothesis. We're wondering, does the mean weight of the males, is it different? So we have this key thing, is it different? So we're wondering, are these different? So mu sub m does not equal mu sub f. So here what we see is that we have two samples. We're looking at means. Do we have known or unknown standard deviations? Well, it says here that the standard deviation of the sample, so nowhere does it say they're populations. These are both samples. So we have unknown population standard deviation, and this is a two-tailed test. So between these first three, what we see is that we want to use a two-sample t-test. So if we go over to the calculator, we can turn that on. We go to stat. We go over to tests. We go down to two-sample t-test. Press enter. Now we're entering our statistics. So we have our x1, our mean. So we're talking, in this case, these would be, say, mu sub 1, and this would be, say, mu sub 2. So for the calculator's sake, we see the subscript of 1 is going to correspond to the males. So we see that there were 10 male infants, a mean of 7 pounds 11 ounces, and a standard deviation of 8 ounces. So the mean, you might be thinking, okay, 7 pounds 11 ounces, what do I do with that? Now, remember, the standard deviation has the same units as the mean, as the regular data values, as everything else that we're using. But the mean right now is talking about 10 pounds 11 ounces. So we want to convert to ounces. So convert to ounces. So we know that 16 ounces is equal to 1 pound. So if we do the math on this, we're going to get 133 ounces. So we put in 133. Our sample standard deviation we said was 8. Our n sub 1 we said was 10. We go down to the second group. So now we have 7 pounds 4 ounces, standard deviation of 5, and there were 8 females. So again, doing the math of converting this will be 116 ounces. So we have 116 ounces. Wait, I think I did that wrong. This should be 123. This should be 123. So 123 ounces. 116. Our sample standard deviation we said is 5. Our total sample size is 8. Our alternative hypothesis says that these two are not equal to each other. Now this pooled option, we will always choose to not pool the variances. So there's an option here about pooling it. Always just press no. We're never going to discuss what that would look like. So now what we have is we have our results pop out. So we have our test statistic. Our test statistic we see is going to be t is equal to 2.27. Our p-value we see is 0.038. So now we compare this to the alpha value that we were given. So since the p-value, which equals 0.038, is less than 0.05, which is equal to alpha, we reject the null hypothesis. So we reject the null hypothesis. There is sufficient evidence. So there is sufficient evidence to believe there is a difference in weights. Okay, so that's good. So we have that from just the statistical side. There is sufficient evidence to believe that there is a difference in the weights. Now if we'd like to go on to Cohen's d. So the formula for Cohen's d, so we have Cohen's d. The formula that we had was we had x sub 1 minus x sub 2 all divided by the square root of n sub 1 minus 1 times s sub 1 squared plus n sub 2 minus 1 times s sub 2 squared divided by n sub 1 plus n sub 2 minus 2. Now this is the formula that I gave you, but I would actually suggest that we put absolute values around this, because sometimes you might get a negative. The negative is only because of which one is called x1, x2. You're free to switch them. So if we do the absolute value, this will give us a more accurate answer. So we will now put this into the put things into the formula. So we can have 123 minus 116 divided by the square root. We said the n1 was 10, so we subtract 1, so we get 9. Multiply this times the standard deviation, which we said was 8 squared. And then we have plus, we said the sample size of the second one was 8, so we subtract 1, so we get 7. Our sample standard deviation was 5. Square that. Divide this by n sub 1 plus n sub 2 minus 2. So we have 10 plus 8 minus 2. That gives us 16. And we will, again, take the absolute value just to make sure that we have a positive number at the end. So now we go back over to the calculator. We clear all of these. So the numerator is going to be 7. We divide this by a square root. Make sure you put parentheses around the numerator of this fraction. So we're going to take 9 times 64 plus 7 times 25. Close that parentheses, divide this by 16, and close those parentheses. So you want to make sure you use parentheses carefully. What we get is we get 1.02. So the absolute value of this is just the same thing as 1.02. So remember, when we looked at Cohen's d, we said those could either be very small, small, medium, or large effect sizes. This is larger than 0.8. So what this says is that we have a large effect size. So indeed, in this case, there is statistical evidence to believe that there's a difference in weight, and also the large effect size so that we could also see this with the naked eye. So you would be able to perceive the difference of the weights between the male infants and the female infants to see that there is a difference between those. So in this case, again, this is the practical significance. And over here, this was the statistical significance. So in this case, if you were doing something more with this data, you would be inclined to make sure that you make changes based on the difference between these two. So indeed, this is what it looks like to see both practical significance as well as statistical significance in using Cohen's d.